which consists in a standalone equipment to collect crime evidence from a scene of crime. And I'm here representing my team from the Federal University of Bahia, and my colleague Computer Araújo and my advisor Luciano. This is the outline of the presentation. Introduction, then I'll talk about the problem, our contributions, details about Air-CSI, they'll show some simulation results, and conclude. Air-CSI is a system that uses out-controlled unmanned aerial vehicle, known as a drone, to analyze the location of the crime. The system is based on cameras and uses these cameras to localize itself without GPS and to detect the evidence in this scene. It contrasts with the situation where the experts have to enter the location. The idea is using the drone to perform a scanning of the whole scene and getting as output the found evidence. The problem addressed here is that criminal evidence are not perennial, they are right, and the evidence needs to be stored and protected as soon as possible. We are interested in a solution to efficiently reduce the state of the crime scene, reducing the need for human interference, and also facilitate expertise in difficult to assess locations, while preserving the crime experts from coming into contact with dangerous artifacts. Okay. Some advantages of using the drone are the wind caused by the propeller, so it must fly above a minimum height, and the top view must be unobstructed. Okay. Our contributions are, number one, the introduction of a method to calculate the trajectory for drone scanning the crime scene, a new methodology to detect the evidence from multiple perspectives, so facilitating the job of object detector, and three, as simulation in a realistic environment. Okay. This is the outline of the system. At the initialization, the drone is placed next to the crime scene, so using the self-localization, it flies until a given height and performs early object detection, which serves as reference to calculate the trajectory. So the control system drives the drone by the trajectory, and this process is repeated for some heights, different heights. And at the end, a report is generated consisting of three parts: a sketch of the crime scene, a list of the found evidence, and the raw images and videos. Just you see the initialization, and it's based on the previous work of my colleague, Pompilio, who called it a video slam method based on stereo image. ASPAI works by extracting features from a pair of images, and by comparing the features, it can match corresponding regions in this image. And since we know the distance between the left and the right camera, geometry can be used to estimate the distance to some key points in this image, and this distance can be used to self-localize the drone in the real environment. To control the drone, we consider 4 degrees of freedom, the 3D coordinates, and the yaw rotation, rotation around the vertical. Because the drone moves in equilibrium and slowly, we can neglect the rotation around the other axis. And for it to coordinate, we have two PID controllers, one for position for the velocity, and it will give us a total of 8 controllers. And each pair is arranged in a cascade group like this. Using control equations, we can calculate the parameters for tuning the controllers. We get this value here and here. We have simulation showing the control performance for each axis or coordinate. Here in the z-axis, the drone goes up. And we move along the x coordinate. In this case, we've got a small overshoot, but it's not a big deal. We think it's due to delays in communication. Moving along the y coordinates. And finally, the drone rotates around the vertical axis. Simulation shows us that the controllers are fine properties. And for evidence detection, we use a deep learning solution. The YOLO-V3 neural network. We could use any object detector, but we choose YOLO because it's fast. And we use the COCO multi-class dataset along with the weapons dataset with around 3,000 images of games. And we have tried two strategies for training. First, we use the pre-training weights from the COCO dataset. So we made a transfer learning. Then we fine-tuned the network with the weapons dataset. And the another strategy was to join both datasets and train all the network from scratch. As we can see here, we obtained better results when training from scratch. This is the average precision. And to calculate the trajectory of drone, we propose the following methodology. Each type of evidence is associated with cover ranges. For example, for the knife, we set 1 meter, and for guns, 2 meters, and the body, 3 meters. These ranges are defined by a crime expert. The values are we use to compute a minimal rectangle that encompasses all the circles. Then we put the vertices of the rectangle in this equation, so we can generate trajectories for each height of flight, so that cover the entire scene. And another benefit of doing this is because we have multiple perspectives of each evidence, so we can improve facilitate the performance of the object detector. Instead of using just the score of the object detector for one image, we can average for multiple perspective images. In order to avoid accidents when testing the system in a real drone, causing damage to it. We test our system in a realistic environment in the simulator, call it Air-CSI. We use the same hardware interface as for the drone, but instead of communicating with the drone, we communicate with the simulator in a computer. And we simulate for two scenarios. The first one without occlusions, and the second with some partial occlusion. The scenario without occlusions you see here on guns, on machine gun, knife, on the body, and with some partial occlusions. The gun is covered the knife, the cone the gun, the ground is the machine gun, and so on. And you can see the number of times each address was detected. In this scenario, without occlusions, the bigger objects were detected from 10 meters and for the lower distance, and the smaller objects for the smaller distance, smaller heights, but all the objects were detected. In the second scenario, because only the human body as a big object was detected from 10 meters of height, and you have a failure here. The knife, the smallest object, was not detected from any distance. But in this case, it's not a big deal because as the gun was detected, the evidence is not lost at all. That's different for the system. And to conclude, Air-CSI is a multitask system comprised of self-localization, low and high-level control, and object detection. Simulations show promising results for evidence detection even in complex scenarios, and occlusions impose some ambiguities, but in practice, crime expert can make some false refinements. Now we are working on training this system in a real drone, and we intend to add new classes of evidence like munitions, projectiles, blue spans, and so on. It's all. Thank you for your attention.
Dataset?
Yeah, we use the darknet implementation
On Linux or Windows?
in Linux.
Okay, thank you.
Yeah.
Sorry. Sorry. Can I continue?
Yeah.
Thank you. For a real-time application, are you planning to make object detection on edge? I mean, your drone, or on cloud, or on your PC? Do you have an idea?
Our plans are using the system embedding all the hardware and software in the drone.
Okay. Okay, thank you.
That's it.
Further question? It kind of looked like you used an Intel ReSense module on the drone. Is this right, or is this just the plan?
Using what?
The Intel ReSense camera used on the drone, right, for the stereo? At least it was in one of the images.
The stereo cameras are used for the self-localization system, but it also has a monocular camera for image detection. And for the evidence detection, the evidence of crime, use the monocular image, but the stereo are used just for the self-localization.
Ah, okay. So you just use it for. Okay. So can the drone actually can it fly with so much weight? Because you use a Jetson TX2 module and then the camera and then the ReSense. Can you check?
Yeah,
It's like, I'm not sure.
Well, now we have some preliminary tests when the
Okay.
drone is flying.
Stably, or it's like, you know,
It's not perfect, but it's fine. we are working with this.
okay.
Further questions, remarks? If not, I have a question. You mentioned you have two images
Yeah.
at the same time. Where does the second image come from? This is on the one camera. It's
No,
missed
no.
it somehow.
Let's see Here we have a pair of stereo cameras, and you have a monochrome camera. This one is used for evidence detection, and these are used for self-localization.
Oh, okay. Thank you very much. If there are no more questions, we can thank the speaker again.